Dipole moment mu is the product of the magnitude of charge and distance between the center of positive and negative charge. Mu equal to q multiplied by r. Q is charge, r is distance of separation. Unit of dipole moment is day by capital D. 1D is equal to 3.33564 10 raised to minus 30 coulomb meter. C is coulomb, M is meter. Dipole moment being a vector quantity is represented by a small arrow with the tail on the positive center and the head pointing towards the negative center. H partial positive, fluorine partial negative, mu is 1.91D. The crossed arrow above the Lewis structure indicates the direction of the shift of electron density towards the more electronegative atom. Dipole moment of polyatomic molecules. Each polar bond in polyatomic molecule has its own dipole. The resultant dipole of the molecule is decided by first shape of the molecule, that is spatial arrangement of bond. Second, contribution of the individual dipole and those of the lone pair of electron. If any, dipole moment of polyatomic molecule is the vector sum of the dipole moment of various bond and lone pair. Consider beryllium difluoride and boron trifluoride. Beryllium difluoride is a linear molecule and dipole are in opposite direction and are of equal strength. So net dipole moment of beryllium difluoride is equal to 0. Beryllium difluoride bond dipole. Net dipole of beryllium difluoride is equal to 0. Boron trifluoride is angular. In boron trifluoride, bond angle is 120 degree and molecule is symmetrical. The three BF bonds are oriented at 120 degree with each other, and sum of any two is equal and opposite to the third. Therefore, sum of the three BF bond dipole is equal to 0. Bond dipole net dipole in BF3 equal to 0. In case of angular molecule, both lone pair and electronegativity difference contribute to dipole moment. Lone pair and dipole moment. In some molecule, the central atom has an unshared or lone pair of electron. This lone pair also contribute to overall dipole of the molecule. Nitrogen in ammonia and oxygen in water possess lone pair. This reinforces the dipole due to NH and oxygen hydrogen bond. Both these molecules are highly polar. Ammonia dipole moment is 1.48 dB. Water is 1.85 dB. Nitrogen has only one lone pair while oxygen has two lone pairs, which reflect in the higher dipole moment of water. Consider ammonia and nitrogen trifluoride. Both have pyramidal shape with a lone pair of electron on nitrogen atom. Here hydrogen is less electronegative while fluorine is more electronegative than nitrogen. The resultant dipole moment of ammonia is 4.90 10 minus 30 coulomb meter, while that of nitrogen trifluoride is 0.80 10 minus 30 coulomb meter. This difference is called in case of ammonia. The orbital dipole due to lone pair is in same direction as that of resultant dipole moment of NH bond, hence get added, whereas in nitrogen trifluoride the orbital moment is in the direction opposite to the resultant dipole moment of 3NF bond. The orbital dipole, because of lone pair, decrease the effect of the resultant NF bond moment, which result in its low dipole moment. Resultant dipole moment, ammonia molecule 4.90 10 minus 30 coulomb meter, NF3 molecule 0.80 10 minus 30 coulomb meter. Resultant dipole moment. Methane. The central atom carbon has no lone pair and molecule is non-polar. In methyl trichloride, the dipole are not equal and do not cancel, hence methyl trichloride is polar with a non-zero dipole moment. Methyl trichloride mu is 1.04. Dipole moment of some molecule are shown in table 5.8. 5.8 dipole moment and geometry of some molecules. Molecule AB, example hydrogen fluoride dipole moment is 1.91, geometry linear. Molecule AB, hydrogen fluoride dipole moment 1.03, linear. Hydrogen bromide dipole moment is 0.79, geometry is linear. Hydrogen dipole moment is 0, geometry is linear. Molecule AB2, water, dipole moment 1.85 is geometry bent. Dihydrogen sulfide, dipole moment 0.95, geometry is bent. Carbon dioxide dipole moment 0 is linear geometry. AB3, ammonia dipole moment is 1.47, geometry is trigonal bipyramidal. NF3 dipole moment 0.23 is geometry trigonal bipyramidal. BF3 dipole moment is 0, trigonal planar. Molecule AB4, methane dipole moment 0, geometry tetrahedral. Ammonium trichloride dipole moment 1.04, geometry tetrahedral. Carbon tetrachlorois dipole moment 0, geometry is tetrahedral. Covalent character of ionic bond. Several ionic compounds possess partial covalent character and show properties similar to covalent compound. For example, lithium fluoride is ionic but it is more soluble in organic solvent than water. To explain the partial covalent character in ionic bonds, Fajan put forth the following rules. The smaller size of cation and larger the size of anion renders greater covalent character to ionic bond. For example, lithium plus chloro is more covalent than Na plus chlorine. Sodium cation chlorine. Similarly, lithium plus I minus is more covalent than lithium plus chlorine minus. Greater the charge on cation, more is covalent character of ionic bond. For example, covalent character of aluminum trichloride, magnesium dichloride and sodium chloride decreases in the following order: Al3Cl minus 3 greater than Mg2 plus Cl minus 2 greater than Na plus Cl minus. A cation with the outer electronic configuration of sp2p6d10 type possesses a greater polarizing power compared to the cation having the same size and same charge but having outer electronic configuration of sp2p6 type. This is because the electron of sp2p6d10 shell screen nuclear charge less effectively compared to s and p electron of sp2p6 shells. Hence, the effective nuclear charge in a cation having s2p6d10 configuration is greater than that of one having s2p6 configuration. For example, copper plus Cl minus is more covalent than Na plus Cl minus. Here copper plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Na plus is 1s2, 2s2, 2p6. 5.8 resonance. Many polyatomic molecules can be represented by more than one Lewis structure. Consider for example 3 structures written for carbon dioxide 2 minus. Each structure differs from the other only in the position of electron without changing position of the atoms. None of the individual structure is adequate to explain the property. The actual structure of carbon trioxide 2 minus is a combination of 3 Lewis structure and is called as resonance hybrid. Resonance signifies that there is more than one possible way in which the electron can be assigned in a Lewis structure. The various structures are called canonical forms. Now consider the example of ozone. It is the resonance hybrid of the following structures. Resonance of hybrid. Resonance in ozone molecule. Structure 1 and 2 are canonical form while structure 3 is the resonance hybrid. Resonance energy. We have seen that many polyatomic ions and molecules can be represented by a different canonical form, and each form has a different energy. Energy of the resonating form is different from the more stable structure. Resonance hybrid, the difference in energy of the stable contributing structure and resonating form is usually defined as resonance energy. To summarize, it can be stated that A. Energy of the resonance hybrid structure is less than the energy of any single canonical form. Hence, resonance stabilizes certain polyatomic molecular ion. B. The average of all resonating structure contribute to overall bonding characteristic feature of the molecule. This will be clear from the example of ozone. Ozone can be represented by two canonical forms shown earlier.